Okay, let's now look at the competitive learning rule, sometimes called the winner-take-all learning rule. So this is an unsupervised network training approach, which is applicable for an ensemble of neurons, meaning that you have at the output a layer of P neurons, not just for a single neuron like the perceptual learning rule that we've seen before. So the outputs neurons of a neural network, they compete to become active. That's why it's called competitive learning rule. And the neuron M, which has the maximum response due to input X, so you basically specialize this neuron M to respond to a certain input. And it competes with the other neurons to be the winner, to be the one which responds to this input, to this particular input. So only a single neuron is active at any one time. That's why it's called the winner-take-all, a salient feature for pattern classification. Neurons learn to specialize on ensembles of similar pattern, meaning that whenever you have a pattern with certain features, in the case of the competitive learning, only one neuron specializes to respond to that type of input or features. So the basic elements of a competitive learning, so you have a set of neurons that are all the same, except of their synaptic weight. So this is your input layer of source input. These are your neuron, a single layer of output neuron. Again, you have P of them, only one winner. So they respond differently to a given set of input pattern. So this one, so if you have a certain input pattern, this one may give the maximum response or be the one which is active or fires. And if you have another type of input or pattern with certain features, maybe this one would fire. So they respond differently to a given set of input pattern. It's a mechanism to compete to respond to a given input, as we explained here. And the winner that wins the competition is called the winner takes all. So he's the only winner. That's why it's called winner takes all. So the architecture is as shown here. So you have your input layer. It is fully connected. And these are the weights from this input to this node. And then, so you have feed-forward connections which are excitatory, but then you have also lateral connections or connections between these output neurons, which are inhibitory. That's why it's called lateral inhibition. So the competitive learning rule works as follows. So the neuron M, which has the maximum response due to input X, is changed. So you have its weight are modified, meaning that if you have a neuron, an input X, you compute for all P neurons, P output neurons, you compute the response, WITX, and you pick the one, the neuron M, which has the maximum response. And then for all the other neurons, you don't change the weights, but for neuron M, you make it closer. So you make that weight closer to the input. So you take a fraction of the difference between X minus W. You make W for WM closer or a fraction closer to your input. We're going to see a diagram later. So the weights are typically initialized at random values. So at the beginning, they're random values and their strengths are normalized during learning. So for example, the sum of all the weights is equal to 1. And that's why, so when you increase the weight for node M. So because their sum is equal to 1, so you're going to basically decrease the other weights. So if a neuron does not respond to a particular input, no learning takes place. So you have delta Wi equal to 0. So in a 3D feature space, for example, let's say you have these features, so patterns which have these features here, and then another pattern with these features, and another pattern with these features. And then you have your weights randomly selected in this space, such that they are the sum of the Wmj square equal to 1 or m. And the idea is, so this is before training. So after training, so you move these weights so that this node would respond to this set of pattern. This node here, this output node would respond to this set of patterns, and then this node specializes to respond to these features or to this set of patterns. So as the caption says, geometric interpretation of the competitive learning process, the dots represent the input vectors, and the crosses represent the synaptic weight vectors. So these crosses represent the synaptic weight vectors of 3 output neurons. And this is before, so at the initialization of the network, and then the final state of the network after training. So what is required for the net to encode the training set is that the weight vectors become aligned with any clusters that are present in this set, and that each cluster is represented by at least one node. So yeah, so you have a cluster here, and then each cluster would be represented by one node. Then when a vector is presented to the net, there will be a node or a group of nodes. So when you have a node, it's just a winner takes all. You can have sometimes a group of nodes which specialize to respond to a certain input. So when a vector is presented to the net, there would be a node or group of nodes which respond maximally to the input, and which respond in this way only when this vector is shown at the input. So whenever you have a certain input, so there is only one node which responds again to your input. If the net can learn a weight vector configuration like this without being told explicitly of the existence of clusters at the input, then you can call it a self-organized network. This is a form of unsupervised learning because you don't have a supervisor which says, oh, okay, there is this cluster, and then you need to, you need an output neuron to respond to that cluster, to specialize to respond to this set of features which belong to this cluster. So this is in contrast with the delta rule, for example, where it was a supervised learning approach. So in order to achieve this goal, the weight vectors must be rotated around the sphere so that they line up with the training set. So you should rotate these weights until they line up with the training set. The first thing to notice is that this may be achieved in a gradual and efficient way by moving the weight vectors, which is closest in an angular sense to the current input vector. So it doesn't happen immediately. So it's a gradual adaptation of that neuron to respond to a certain input. And the node K with the closest vector is that which gives the greatest input excitation. So the one that responds maximally. And as shown below with this equation, the weight vector of node K may be aligned more closely with the input if the change is made according to this formula. As we've seen here, this is the learning rule for the winner takes all. Okay, in a vector form, you can see here, if you have your input vector X, this is your weight vector W, and this is the X minus W, and then you move the W, so that this is W plus delta W, or the new weight, a fraction of the difference between X, between the input and the weight. And you keep doing it until you align your weight with the input. And so, as I said, this is a winner take all, but then sometimes this is extended beyond a single neuron winner. So it's not just one winner to include the neighboring neurons. So you have neighboring neurons which specialize to respond to a certain input. Summary of the learning rules. So we've seen, for example, the Hebbian rule, the perceptron learning rule, the delta rule, the withdraw half rule, the correlation rule, and the winner take all rule, which is the last one, the competitive one. So this is the way you adjust the W. So every time you have your new W is equal to the old W plus this delta W. And this is the formula for the Hebbian. This is the formula for the perceptron and so on. This is the way, or the recommended way on setting your initial weights. So for the Hebbian rule, it's good to set them to 0. For the perceptron, so you can have any set of rules, even randomized, and correlation is 0. And for the winner take all is random but normalized. The learning rule, the type of learning rule, so you can classify it under supervised for S and unsupervised. So all of them that we've seen are supervised. They need ground truth. They need labels for the output, except the Hebbian rule and the winner take all. The type of neuron that you can use. So any, meaning it can be binary, bipolar, binary, unipolar, or continuous. This is what any means. But then for the perceptron, it is binary bipolar, or binary unipolar. For the delta rule, it works for a continuous neuron, and then the withdraw, and then these ones are shown on the table. For the neuron versus layer, so all of them apply to a neuron. So for example, for the perceptron, you can have just a single perceptron, one neuron, and you can make it, learn. As opposed to the competitive learning rule, which requires a set of neurons, P neurons at the output layer. Thank you.